Hello. So let's continue our discussion on the Maxwell's equations, and we are going to study the third law or third equation of Maxwell. So the third law is called as Faraday's law of electromagnetic induction, and there are again two forms for this equation or this third law: differential form and the integral form. So let us have a look at this figure first. So what we see here, we have this solenoid, or let's say a coil with a number of turns indicated by small n, for example, and we pass an alternating current through this winding or a coil. So because of that, there'll be a alternating magnetic field indicated by the green lines that is occurring into this coil. So these magnetic field lines, or in other words, we can also call it as magnetic flux, which is time varying. When take another wire in the form of a loop, you take that wire, which is in the form of a loop, in the close vicinity of these magnetic lines. So some of these magnetic lines or an effective magnetic flux are passing through the wire of loop. So because of that, it will induce, this effect will induce a charge carriers flowing through this wire, which is in the form of loop. Or in other words, there'll be a current that will start flowing in this wire. So if we cut this wire, we can have an open circuit and we can connect the voltmeter across it and measure the voltage. So this is the principle of electromagnetic induction. Again, take a solenoid or a coil, pass an AC current through it that will produce an AC alternating magnetic field, which is, in other words, time varying magnetic field. When those magnetic field lines passes, when another wire or a conductor in the form of a loop comes in contact with those magnetic lines, then those magnetic lines will induce an EMF into this conductor. So this is the principle of electromagnetic induction. So in the differential form, we can write it del curl E. This cross sign indicates curl. Okay. So that's the cross product actually. So del cross E is the electric field that will be produced when there is a change in the magnetic field. That is del B over del D, and it will be having the negative sign. So it will be the negative of the rate of change of magnetic field. So how to read this? A changing magnetic field induces an electric field. Just in one sentence, you can define this law. So del B over del T is partial derivative of the magnetic field with respect to time. Okay. So basically electromagnetic induction helps us to predict how a magnetic field will interact with an electric circuit to produce an electromotive force, EMF. So when we are measuring the voltage here, in the physics terms, we can call it as an electromotive force, that is EMF. Now moving on to the next slide, again we have this differential form of equation. Del cross E will be produced, which is nothing but electric field gets produced when there is a change in the magnetic field. And how to read this equation? We can read that the electromotive force or EMF around the closed path, around this closed path in the picture is equal to the time rate of change of the magnetic flux or magnetic field enclosed by the path. Whatever the magnetic field gets enclosed by this path, that will induce an EMF into this electric circuit. And that is mathematically, this equation can be written in this form, and theoretically we can read this way. So where the application of this principle or the third law? The transformers, you have primary winding, you have a secondary winding. The inductors, you can see there are inductors here. We have seen passing the AC current through it. It will generate the alternating magnetic field, and changing magnetic field when take it near to a conductor, that will induce an EMF. And electric motor also, electric generator also uses this principle of electromagnetic induction. So we have understood how to express this law, third law or third equation from Maxwell, which is also called as Faraday's law of electromagnetic induction in its differential form. So remember, this is a differential form equation. How about the integral form? And they are analogous, they are equivalent. Both differential and integral form of all the Maxwell equations are equivalent to each other. So for a, we can say that for an integral form of this equation, we can say that for a loop of a wire in the magnetic field, the magnetic flux can be written in this form. So what we say, for a loop of wire in a magnetic field, so this is a loop of a wire, okay, that wire we take it in the magnetic field. See, these green lines are the magnetic field lines. They are coming in contact with the loop of wire. So the magnetic flux, in other words, is equal to the surface integral of the magnetic field lines over the surface area of the loop of wire. So here phi b is the net magnetic flux that gets produced. Double integral summation of t, we are saying that the area is changing over the loop of this wire, and in that, over that area, we are taking the dot product of the magnetic field lines, and the dA is the area element of the surface area of the moving surface. Okay, now integral form, again the equation is given right here, and we can read this equation in the mathematical form. Phi b equals to double integral over the surface area element and the dot product vector of magnetic field and the surface area. And in theoretical, in the words, we can read that this equation can be read as a loop of wire in a magnetic field will produce the magnetic flux. Very simple. The loop of wire right over here, we have these green lines in the magnetic field. Take it near to it, it will induce a magnetic flux. And the magnetic flux will, it is time varying also, will generate the EMF in the coil, okay, in the wire. So the magnetic flux through the wire loop is proportional to the magnetic field lines that will pass through the loop. You see, in this loop, number of green lines, which are the magnetic lines, will pass through this loop, and that will generate that magnetic flux in the loop. And the magnitude of that magnetic flux, again, the magnitude of that magnetic flux, which is phi b, is proportional to, directly proportional to how many magnetic field lines passes through that loop. So now, after understanding the principle of electromagnetic induction, we know that the EMF across this wire will be generated, which is nothing but the electric field, or in terms of physics, we call it as an electromotive force that can be measured in terms of a voltage by this connecting the voltmeter across this wire. How to measure the magnitude of this voltage and the direction of the voltage. The magnitude can be measured by connecting the voltmeter, and the direction we'll see how to measure it. So again, the changing magnetic flux or the magnetic field will produce an EMF in this coil. In this coil, mathematically we say that epsilon is not epsilon, we can say E, or let's say is a special symbol here that indicates the EMF induced in that coil, and it is proportional to or equal to negative rate of change of the magnetic flux phi b. So here is that picture again. we have this equation of magnetic flux and EMF induced. So again, negative. So once the EMF is induced, is generated, we can measure the voltage, but we want to know the direction of the induced EMF, whether it is in which direction this EMF will be induced. So for that, we can use the left hand rule. So take your left hand, turn your fingers upwards, inwards as shown over here, and make the thumb straight up in the direction as shown. And then you can see that you have a red line indicating the vector quantity of magnetic field. And because of that, you can form an angle and indicates your vector normal to the surface of the coil. Okay. So what we see here, we know that there should be a change in the magnetic flux. The constant magnetic flux will not induce any EMF. There should be change, or you can say the magnetic flux that should be time varying, or that's why we write d by dt. Okay, time varying, or magnetic flux is varying with respect to time. So if this change, which is indicated by del phi b, how to calculate del phi b? Take the magnitude of initial flux and take the magnitude of final flux, subtract the two quantities, and if that effective value is positive, which is if the delta phi b is positive, then the curved fingers show the direction of EMF by the yellow arrowheads. You see, this is the yellow arrowhead is indicating the direction of the EMF generated. If the delta phi b is negative, let's say this theta, we calculate the theta, and with that we calculate delta phi b, we just say that the delta phi b is negative, then the direction of EMF will be opposite to these yellow arrowheads. So it will be just take the direction in opposite direction. Okay, so that's how we can determine the direction of the induced EMF. So that was the explanation in detail to explain the third law, or the third equation of Maxwell, which is also called as famously Faraday's law of electromagnetic induction.